Okay, so I guess I can start. So in the last lecture, we saw that just by putting a quantum field theory in AdS, we naturally define a set of correlators that satisfy almost all axioms of a conformal field theory. So I should actually be more precise. I should probably erase this word field, because this was really not a field theory. This was not a local theory. It didn't have a stress tensor. So it was just a set of correlators that had a convergent OPE, and it was and had conformal invariance, and they could even have reflection positivity if you choose a quantum field theory that is reflection positive to start with. So this is what we saw. So we already know that there's a problem. There's no stress tensor. But I want to do here an exercise that shows that indeed this theory does not make sense as a field theory, so a quantum field theory in AdS cannot be dual to a field theory on the boundary, okay? And so to see that, we'll just put this theory at finite temperature and see what happens, okay? So let's go to finite temperature. And let's compute the free energy of this theory. Let's actually look at the free limit, okay? Not even interactions. So this partition function is just usual partition function. So it's the sum over all states of the theory, e to the minus energy 1 over t times the energy. So what's the energy of a state in this theory? So it's a free theory, so it's just the energy of a multi-particle state is just the sum of the energies of each one of the single particle states. So basically, we can say we put k1 particles in the first single particle state, and then we can put k2 particles in the second single particle state forever. And so we have to sum over how many particles we put in the first single particle state, how many particles we put in the second single particle state, and so on. So clearly, I can write this as the product over all single particle states as the sum k from 0 to infinity. Actually, let me use q to the k energy of the single particle state psi, where this q is just e to the minus 1 over the temperature. Okay, everybody agrees with this, I guess. And so, of course, I can do this sum. Okay. So let's just go back to our formula for f. So f was minus the temperature times the logarithm of z. So it becomes the sum over all single particle states of the log of 1 over 1 minus q to the energy of each single particle state. And now I'll just use a trick. So I'll write this log So I'll continue here. I'll write this log just as a series expansion, okay? I will expand in series in this parameter, so q is less than 1, so that's a convergent expansion. So that just gives me this sum, and then n from 1 to infinity, 1 over n, this q to the n e psi. Okay, I just replaced the log by the series expansion, and now I can exchange the sums. And so this sum, this is just minus t, sum n equals 1 to infinity, 1 over n q to the n. Where this z1 is just the single particle partition function, just the sum over all single particle states, q to the energy of the single particle state. Okay? So we just have to compute this now. So this is actually very simple, because what are the energies of a single particle state? Okay, associated with this single scalar field in AdS, we already saw that. So this is just, so probably I can write it. So what are the energies? The energies are just delta, the ground state energy, plus the number of descendants, like the number of p's that you act in each direction. So if you want is like an integer n1 plus n2 plus dot 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 plus nd, the number of each one of the p's in each direction, and then you just have to sum over n1 from 0 to infinity up to nd from 0 to infinity. So again, it's just a trivial geometric sum, so you just get q to the delta over 1 minus q to the d. Good? Is this clear to everybody? Good. So now let's just take the high temperature limit. Okay? So let's compute what happens to this free energy in the high temperature limit. So Q goes to 1 at a very high temperature. So you just have to take the limit here. So I'll just do it directly. So let's look at the free energy. You have this minus t. Sorry, it's still there. Sum n equal 1 to infinity. And now what you're going to get? So Q goes to 1, so this term doesn't matter. Here it's important how it goes to 1. So if you expand, you will just get 1 over n. And from here you get, it was Q to the n, so you get n over t to the d. 1 over n over t to the d. So the conclusion, sorry, this is high temperature. Okay. So you get something like minus zeta function d plus 1 times t to the d plus 1. Right? Is this reasonable? Can anyone see a problem with this result? So what's the free energy? So if I have a conformal field theory in d dimensions, so actually let me do one more step to make it more explicitly. So let's look at the entropy. So the entropy is just df by dt. So it's just it's some number t to the d. Is this reasonable? So if I have a d-dimensional CFT, the entropy should be an extensive property, right? In at least at high temperature. Okay, so it should be given by the volume, which, okay, here I'm setting R to 1, but let's say R to the d minus 1, the spatial volume, times the entropy density. So the entropy density, by dimensional analysis, must be proportional to temperature to the d minus 1. Okay, so entropy density. So clearly you have the wrong power. Okay, so this is just a trivial fact that we were doing quantum field theory in AdS, So it's in AdS, but as long as it's d plus one dimensional quantum field theory, it's still the entropy density at high energy, at high temperature, still scales like a d plus one dimensional quantum field theory, not like a theory in the boundary. Okay, so this is just another manifestation that the dual to quantum field theory in AdS, it's not a local theory on the boundary. Any questions about this? Okay, so we need to put gravity into the game. So let's do that. So let's just consider the simplest theory of gravity. So I'll write this action of, let me write the metric as a capital G because I want to reserve small g to the boundary metric. Yeah, actually let me couple immediately to this scalar field so that we have a bit more structure. So this is just a standard action, d plus 1 w, and let me say here square root g, the Ricci scalar minus some cosmological constant. And okay, I want to put here this scalar field so that I can continue computing some correlators of scalar operators. And I'll just put here the g Newton, and I'll write it in terms of the Planck length so that we keep track of the dimensions of the Planck length. Okay, so this is always a length like that. So we could play so I should also say that this cosmological constant is related to the radius of AdS, right? So there's some constant d minus 1, it's negative 2 over r squared, the radius of AdS. Okay, so these are the two parameters in this theory. It's the Planck length and the radius of AdS. Okay, so why am I saying the radius of AdS? So in principle, this is background independent. I'm not saying what's the geometry, but of course there is a solution of this theory which is just AdS. So we can just take our standard metric, and in fact, so here we could play a similar game to what we did before. We could just say the metric in AdS, sorry, the metric here is just AdS plus some fluctuations, some alpha beta dw alpha dw beta. Okay, so where this, well, this is, I was using mu for boundary indices, so alpha and beta run from 1 to d plus 1. Okay, so this is just bulk indices, and so we could study fluctuations of the graviton on top of this AdS background, and then we would see that single graviton states correspond to the states created by the stress energy tensor and its descendants, and we could look at multi-particle states. It's just created by several stress tensors. Okay, so the same kind of game, but here it's actually better, a bit more instructive to consider the partition function of the theory as a function of the sources. Okay, so what I'll do is that basically maybe I should still use this. I can still write there. Yeah. So I'll just all the correlators that I was talking about before. In this case, I can compute correlators between scalar operators and the stress tensor, just as functional derivatives. So let me just introduce this notation. Actually, I should probably put here. of the log of the partition function as a function of the boundary metric and of a source for this operator O. Okay, so this will be like the connected correlators. So this, this partition function has a meaning in the CFT by itself, right? You put the CFT on a generic metric, G mu nu, and you turn on also a source, so you also deform your action by, well, you can think of it, maybe I should write it as e to the phi b of x, O of x, d dx, but computed also, square root g d dx, computed with some curved metric G mu nu, right? This would be a CFT calculation that computes this partition function, and then you could derive the correlators from there. Okay, so the statement of AdS CFT is that we can also naturally, from a theory of gravity in AdS, compute this partition function. Okay, so as before, I was doing this logic of put quantum field theory in AdS, and then it's a natural construction to consider this limit of the correlators when the points go to the boundary. You get conformal correlators. So now here, there's also a natural construction. So I'll define this partition function as a function of sources as the bulk path integral. Okay, so over all metrics and all scalar fields phi, e to the minus I of g and phi b and phi, with the boundary condition that the metric g goes to the metric at the boundary and the field phi goes to the field phi b at the boundary. So let me be more precise about these boundary conditions. So what does these boundary conditions really mean? So it means that you impose that the metric at large z is just asymptotically AdS. So it's dz square over z square plus, and now you put here dx mu g mu nu of x. So the boundary metric is prescribed by you. It's one boundary condition plus terms that are smaller when z goes to 0. Okay? So that's one boundary condition for the metric that you impose when you do this path integral. And you also impose the boundary condition that the field phi, so it's in AdS, so it depends on z and x, goes like z to the d minus delta times this phi b of x plus terms that are smaller when you approach the boundary. Okay? Is this clear? Okay? So, first consequence of this is that the correlators you generate here already obey the word identities of the stress tensor related to diffeomorphism invariance, right? Related to translations and rotations, because this construction clearly only depends on the metric, on the geometry that this metric creates. It does not depend on the specific, it's invariant under change of coordinates on the boundary. Okay? This boundary condition is invariant under diffeomorphisms of the boundary. Okay? But to have a CFT, we need more, right? There are more word identities that we need to satisfy. So in particular, if we could prove that the partition function as a function of this boundary metric and source for the scalar field was Weil invariant, okay? So here, what's the right scaling? Right, so if we could prove this, then all the other conformal conformal word identities would follow. Right? That's, I think, actually, it's in my notes, but actually I think David also showed this in detail, right? That the conformal word identities follow from this Weyl transformation property of the correlation functions or the partition function, right? From here, this transformation property of the source, of course, implies the correct Weyl transformation properties of the correlator defined by this functional derivative. Okay, so that's the question. Is this true? Given this definition as a path integral in AdS with these boundary conditions, is this true? So let's some color. So let's check. So what happens to the boundary conditions when let's try this identity. So the question is, can we remove omega from these boundary conditions? You see, here the action for gravity in AdS is invariant under change of coordinates. Okay, so what we should try is there some change of coordinates that actually can absorb this factor omega, such that actually the integral does not depend on omega because it's equivalent to put an omega or not. It's just a change of coordinates. Okay, can we see that? So it's clear what you should try to do, right? You have here omega square divided by z square, and here you have z to the d minus delta with omega to the same power. Okay, so it's clear that you want something like, I don't have space here. Okay, so I'll continue there, but you look here. It's clear that you want to do this change of coordinates. Z goes to omega z. Right? If you do that, it's almost perfect. But of course, you pay the price because this also depends on x. So dz will also generate an extra term in the metric of the form dz dx mu, and you will be violating the form of the boundary conditions. Okay. Is it clear what I'm saying? So you need to improve on this, but actually you can improve order by order. So the first terms are just the obvious ones, but then these extra terms that are generated, you can just correct them. So you should do this exercise. So the next two terms, then you can compute more. Okay, so the statement is there is a coordinate transformation, okay, of z and x that actually brings that boundary condition with the omegas to the boundary condition without the omegas. Okay, so we're done. Nobody complains? Where's the Weyl anomaly? Good. Good. So we would be done if actually that integral was finite. Okay. So unfortunately, or whatever, importantly, that integral is not finite. So we need to regulate it. And and the regulator is the usual story. So you have your z equals 0 is the boundary, and so you cut your space-time some epsilon away from the boundary, and so you do your integrals in dz. You only integrate from epsilon to infinity, and so this epsilon is a regulator because actually that the integral, even the classical action, diverges when you do the integral over all space-time. So you have to stop at some epsilon. Okay. But in fact, and now you see the problem, right? The problem is that this coordinate transformation does not preserve the regulator. Okay. So although it looked like we were removing omega from the boundary conditions, we are not preserving the form of the regulator when we change this. When you do this change of coordinates, so actually we're getting a different path integral, a different partition function when we do this change of coordinates. Okay. And in fact this is crucial. Okay. So let me just write that. So change of coordinates does not preserve regulator. And so this leads, like someone said, to the conformal anomaly. Which basically means that the trace of T mu nu is different from 0 in general, in particular in even dimension. But this is actually not important for our discussion, because this is really a UV effect. So it's something completely local, and it does not affect correlation functions of operators at separate points. This is an effect that basically only affects contact terms in the correlation functions. Okay, so in particular. So this is in particular the most important point is that we still have the integral form of these word identities, right? If you remember, that's actually the word identities that David was showing you. So if you compute, so the word identities as effects always at separate points, right? So you do this integral of correlators let's say over some boundary of some region B, and then this basically the word identity. You see here, the points are always separated. You're just integrating around some ball, so some boundary of some ball that contains some of the points, some of the x1. So x is being integrated here. Okay, so this just gives the variation. Right, gives the sum over all points inside this ball. Sorry, this is just the same. Always the same correlator. Right? You've seen this before. It's the integrated form of the word identity. Okay, so I mean, there's a very nice story here that you can actually regulate this. You add to the action some counter terms that only depend on the metric on this boundary surface, this regulated boundary. So you add like the integral of like the area of this, or the integral of the Ricci scalar on this boundary, okay? And so you do that and you subtract all the divergences, and then you can derive the conformal anomaly. So there's a very nice story on that. You can look, it's usually called holographic renormalization, okay? And you match all the expectations from conformal field theory. But I don't want to go into that because that's really a UV effect that does not affect the correlation functions at separate points, which is really what we're interested in. So I'm just happy that we have conformal field theory. So now the last axiom is also here, okay? We have a stress tensor, and it obeys all the word identities that it should. Sure.
Why do you consider that satisfactory? You're not worried about the convergence, or that it wouldn't work in some orders?
You mean that that this is not in closed form, that is yeah, I consider this perfectly satisfactory because that's also a boundary condition. It's just the leading order term that matters. So for a given metric, you can find this coordinate transformation. Yeah. And then you can check in specific cases. So I'm giving you this argument, but you can regulate, get the finite piece, and then check that it's invariant, like I'm saying. Okay. So where I'm a bit lost. Yes.
So you're saying if you expand the metric about the AdS solution and then do this argument in terms of the gravitons, it'll change the scaling?
No. So here, very good. So suppose I do exactly this same argument in terms of gravitons. It will not change the scaling, because if I'm assuming that gravitons can be free up to arbitrarily high energies, okay? So the trick is that at very high energies, what actually is happening in AdS is that it's not that you have a gas of particles, free weakly coupled particles. You just have a big black hole, and then this works. Okay? That we'll probably see next lecture. Maybe this lecture or next lecture, I'm not sure. Okay, but but I wrote this path integral over all metrics. What is this? Nobody complains. This is schematic, right? We don't know how to compute this path integral. Otherwise, maybe I shouldn't study the CFT. Quantum gravity would be solved already. So what we know how to do here is to do a classical limit, right? Or a semi-classical expansion, okay? So what happens? What is the classical limit here, right? The classical limit is when you take the regime where the radius of AdS is much larger than the Planck length, okay? So you have this very big box with a tiny Planck length. So in this regime, Z can be approximated. So the partition function you can approximate just by the on-shell classical action. And moreover, this on-shell classical action will be proportional. So if you see, it's not here, it's behind. You see you have this coupling constant 1 over L Planck to Z minus 1. But then once you replace AdS plus small fluctuations, or if you want to replace this type of metric, basically R to the D minus 1 will come to the front of the action. And so the dimensionless parameter that you have always in front of the action, it's R over L Planck to the D minus 1. Okay? And so in particular, this implies that in the semi-classical limit, if you look at connected endpoint functions of the stress tensor, they will all scale like R over L Planck to the D minus 1. Okay? So now you should remember that for large N CFTs, this was scaling like N squared, right? So here you have the identification that n square should be identified like r over L Planck to the d minus 1. Okay, I think I need to erase now. What should I erase? I think I can erase this. Sorry. Okay, I'll do it. So, what do I mean by that? I mean, okay, let's not lose the logic. So the logic is I'm starting from AdS and I'm trying to construct this partition function as a function of the boundary conditions, and this is naturally has all the properties to be the partition function of a CFT. Okay, so what I'm saying is that more precisely in the semi-classical limit, it has all the properties to be the partition function of a large n CFT if I identify n square with that ratio. Sure, sure. Resolution of? The resolution is that in this partition function, I assumed that when I put AdS at high temperature, the state is described by many weakly interacting particles or many free particles. That is not true. When AdS sits at finite temperature, at high temperature, the state that dominates the path integral, it's a big black hole. So just that counting does not apply. If you have gravity. If you don't have gravity, then it's what we did, and it's not a CFT. Does it make sense? You could, and then there is an intermediate regime of temperatures where you can see where the CFT looks like a d plus one dimensional theory. That's true. Yes. There's actually several regimes of temperature. I recommend you go and read this so what should I recommend? Yeah, that was a very nice story. There's meanwhile Wiseman and Papadodimas and more people about thermal properties of AdS, and in particular, say n equals 4 super Young Mills. And there's several regimes where first AdS starts to be just a gas of weakly interacting particles. Then you increase more the temperature, you start to see that particles are actually strings, and strings become very stretched. You start to excite each one of the strings, and you have Agathorn growth in the number of states. And then you transition, like there's a first order phase transition to a big black hole. But okay, depending how if you go fixed energy, fixed temperature. It's a very nice story. I recommend you go and read about that. Yes. Was a free theory, yes. Yeah, that's a good question. So good. You can always now try to compare interaction strength versus the temperature, but in general, the answer, I think I don't really have a good answer to that question. No, let's see. The intuition is, suppose you have quantum field theory in a box, okay, with like just reflecting boundary conditions. Then, whatever the interactions, you expect the entropy density to be proportional to the volume of the box. Okay, so this is what the result is saying, is that the quantum field theory in AdS is proportional to the volume of the box, which is AdS, which the sizes are the radius of AdS. Okay, so this is what the result is saying. So we can only do the computation exactly in the free theory, but I expect this to be true for any quantum field theory in AdS, because it's just the fact that you have an extensive quantity of some box, so it's volume of the box times the density, and then it's just dimensional analysis. So what do I want to say next? Okay, so let me just introduce. What time is it? Okay, let me introduce more precisely. Talk about the two-point function of the stress tensor, because it's a very universal object. So the two-point function is always basically completely fixed. In a conformal field theory, it's always completely fixed by conformal symmetry. Okay, so this is basically a fixed tensor structure, which you can write very easily as mu alpha, mu beta plus, let me put a half, mu beta, mu alpha, minus the trace. Okay, so this is just a tensor structure fixed by conformal symmetry, and this constant here in front is usually called CT, and the normalization is SD square, x square to the d. Okay, so, well, let me just explain that. So this SD is just a volume. There's some formula. So 2 pi d over 2 over gamma d over 2. So this is just the volume of a unit sphere. Okay, unit SD minus 1. So this is just a convention to measure this CT. So this two-point function of test tensor, this constant, is, if you want, is a measure. So it's a good measure of the number of the local degrees of freedom. Okay? Not in the sense that it's something that always decreases and that RG flow. Okay, not in that sense. Just in the generic sense that if you have a theory with many degrees of freedom, CT will be large. Okay. In particular, I think I have some formulas here. So CT, if you have like free scalar field, CT will be, so for each scalar field, you get some d over d minus 1. And for each free Dirac fermion, you get that formula. Okay, so it's just some way of counting how many degrees of freedom you have. So in particular, you can compute this two-point function of the stress tensor using the gravitational description, right? So you just have to compute. Okay, I erased. That was a bit stupid. You just have to compute this partition function to second order in the metric fluctuation around flat space, because then you take two functional derivative to get the two-point function. And so this has been done by Liu and Zeitlin in '98, and as expected, you get CT to be given. There's some precise number, some gamma functions. Okay, I will not write, but it's something you know exactly. Depends on dimension, and then, as we already said, depends on this ratio, like that. So again, this is just one particular case, but I wanted to define it because then I want to say something about it very specifically. That tells you that the CFT dual to a semi-classical theory of gravity in AdS has to have a very large number of degrees of freedom. Okay, so if you want to describe a very big universe with a small Planck length, you need many, many, many degrees of freedom at the boundary. Okay, that's what this is telling you. Sorry? No, this was just for simplicity. I had to put gravity to have a stress tensor. Now I put a scalar because I wanted to have this kind of interplay between conformal word identities and the stress tensor. But yeah, I could even do pure gravity. That's actually what I will talk about. What I will talk about now. Yes, exactly. Sorry, yeah, maybe that was your question. I'm sorry. So, no, sorry, yeah, good question. So for this calculation, so this is AdS, gravity. For this calculation of CT, like the matter content of the theory doesn't matter in AdS. So you really just, because it's just the quadratic term in the metric fluctuation, so you don't get any contributions from the matter fields. At leading order at large n, right? You could start to do bulk loops, but that would be much smaller than this effect, right? It would be suppressed by n squared. Okay, so now let's discuss some philosophy, more or less. Let's see. So what have we learned so far? We learned that if we study gravity in AdS in the regime where we know how to compute gravity, which is the semi-classical regime, we get CFT correlators which have all the properties of the CFT. Okay, now it's all, but it's of a large n CFT. So it's not an exact CFT, it's an expansion. You have to take a family of CFTs and you have a large n expansion that corresponds exactly to the correlators you get in semi-classical gravity. So of course now the natural thing to say is, okay, if I really want quantum gravity at finite Planck length, okay, so like big number, R over LADS, but finite, so that I can include loops, some non-perturbative definition. So maybe I can just use a CFT at finite n, and that's it. That's a definition of this path integral. It's a CFT at finite n. Okay, so this is the philosophy. So, but what CFT? Any CFT will do. Will any CFT be a good CFT to define quantum gravity? Okay, depends on your taste. Let's see. So what do we mean? So this leads us to the second question. What do we mean by quantum gravity? Okay, quantum gravity in a very loose sense, like a theory of a dynamical metric. Then I think the answer is yes. Any CFT, in some sense, it's a theory of quantum gravity. Okay, but that's not very useful for the world we live in, right? We want a world where gravity, it's basically general relativity. So what we want is just some UV completion of general relativity, right? Our world is very different from higher spin theory, right? We don't have higher spin massless fields, okay? So in that sense, I want to know what CFT can be more closely related to gravity as we see it, okay? So my definition for this discussion, but okay, that's just to create some discussion. Let me actually talk about, let me call it pure quantum gravity. I'll just say it's a UV completion of general relativity. Okay? So what do I mean by that? So I mean that actually I want to do pure, so let's not put no extra light matter, okay? Let's just have gravitons, okay? Let's not put any matter for now. So what should we require about a CFT, okay, that can be a UV completion of quantum gravity, okay? So we already know if we want to study quantum gravity in a large AdS, right, because we want to see something similar to our world, then we need this large n. No, sorry, this is not what I want to say. I'm sorry. Sorry, I don't want to talk about CFT for now. I'm sorry. CFT is afterwards. Forget about CFT. Suppose just the problem of I want to find a UV completion of general relativity. Okay, what is that? The only thing I really need to impose is that it has the same low energy spectrum, right? So it's a UV completion. So I don't want to change what happens at low energies. That's predicted by GR. I want to keep the same graviton spectrum in AdS, and I also want to keep consistent quantum mechanics. Okay? Basically, those are the two real requirements. This is required. Now there are other things that I would like to have, which is, for example, that that the leading behavior of the correlation functions of the stress tensor, okay, defined by that limit, by that partition function, is given by GR in AdS. Okay? So I should also get that, because that's a low energy observable. So if I'm just UV completing quantum gravity, I should also get that. But actually, this, I don't consider this a requirement. I consider this, if you want, desirable. This should follow from this. I think that's the common understanding, right? That if we have a theory of gravitons, okay, then the only consistent interactions are the interactions given by general relativity. Okay, so this is okay. I want to make this point. And another thing, for example, that you might want to, there are other properties of GR that you should be able to find. For example, you should get, for example, this thermal behavior. For example, high energy density of states, for example, given by black holes in AdS, by the Bekenstein-Hawking formula of black holes in AdS. For example, that should also be, once you UV complete quantum gravity, you go to very high energy states, and you see that the entropy density is given by black holes. That should also follow from this. And there's other properties, many other properties, that we would like to prove that in any UV completion of gravity, of general relativity, they follow. Okay. Any question about this philosophical remark? Okay. Okay, so, but now we have a definition of what a UV completion of general relativity is, at least in AdS, right? It's just a CFT. Okay, so we can just transform these loose statements into precise conjectures for conformal field theory. Okay. So what is the statement? So I want a CFT with some SUN, for example. Well, this actually, it's not a requirement, but that's like the simplest way of thinking about it. With some large n, so that we can take large n. And the most important requirement is that T mu nu is the only single trace operator with delta of order 1. Okay? So basically, all the other single trace operators have to have very, very high dimension. Otherwise, you would not be UV completing just pure general relativity. You would have extra light degrees of freedom. Okay? So clearly, it's a super strong requirement. Right? In any adjoint theory, we can write infinite number. Right? If it's weakly coupled, we can write an infinite number of single trace operators just by taking trace of lots of products of 5. Okay? So this is a very strong requirement that implies that the theory must have strong coupling. Okay? So that makes it immediately very difficult to study this kind of CFTs or even to find one, because it must be very strongly coupled. Okay, but let me just say, so this, let me call then delta gap the dimension of the lightest operator with spin greater than 2. Okay, so this is this would be the minimal requirement is that all operators that have higher spin have to have very high dimension, because we know if they have low dimension, then these operators of higher spin, they just come as an infinite set, like Simone was explaining, and so this will completely be different from general relativity. Okay, so one thing that you might want to try to prove, or if you want to conjecture, so let me say conjecture, is that if you find a CFT that satisfies these properties, then the endpoint functions of the stress tensor are just given by n squared times the prediction from GR plus corrections that are suppressed by this delta gap. Okay. Well, plus order n to the 0. So this is, for example, one conjecture, that the spectrum and the large n structure fixes entirely all the endpoint functions of the stress tensor. Yes?
Did you mean T nu is the only single trace operator with spin less than or equal to 2?
No, here I want to be stronger because yes, conserved currents are not allowed in this definition of pure quantum gravity. Okay, because as I said, I want to describe something which I can take the flat space limit, so the radius can be very large compared to the Planck length. I just want to have gravitons. Okay, so can we prove that? We cannot prove that, but we can prove, it has been proven actually, up to some subtleties, but basically proven, for the case of the 3-point function. So for the case of the 3-point function, Simon already mentioned, so in d equals 3, there are only two structures that can appear, two tensor structures that can appear in the 3-point function of stress tensors. But in higher dimensions, there are 3 structures in general. And of course, if you do the computation in AdS, Einstein gravity predicts a specific combination, okay? Predicts a specific structure. So the question is, can you show that those assumptions on the spectrum of the CFT force you to have only that combination? And basically the answer is yes. So the first argument was not actually directly a CFT argument. So it was in a paper last year by Maldacena, Gibodeov, Edelstein, and Camagno, where they studied this problem just from the gravitational point of view. And basically they showed that causality was violated if the 3-point function was not exactly given by general relativity. So the as I said, there's 3 structures. So there's a structure that comes just from GR. So let's say from the Ricci term in the action. And then you can have more structures. So for example, with some coupling, well, okay, let me just write. Yeah, with some coupling alpha 2, which is associated So you can generate this structure in AdS if you add to the action, okay? Instead of just having Ricci scalar, you can add higher curvature correction. So like a term like R square. And you can also generate the third structure if you add to the action a term like R cubed, okay? Some combination of Riemann cubed, okay? And so what they showed is that this action, even at the classical limit, does not make sense. Like it violates. You can study graviton scattering and see that it violates causality. Like you can get negative time delay if these numbers are not very small. So in particular, they actually showed that these numbers, so alpha 2 has to be smaller than 1 over delta gap square, and alpha 4 smaller than 1 over delta gap to the fourth. And more recently, Maldacena, Schenker, and Stanford, they have this argument, a bound on chaos, that actually implies precisely this. For the, if you translate their result to a statement about CFT 4-point functions, and in particular the decomposition in 3-point functions, it implies this result. Okay, so actually I think Juan talked about this last week. So maybe you know more than me about that. Okay, any question? Okay, enough of this, because what you should complain is, well, this is blah, 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 blah. Is there any example? Can you find a CFT like that? I don't know. I wish I do. I don't know. It's an open question. Can we UV complete GR or not? Can we find an explicit example of a CFT with these properties? I don't know. It involves strong coupling, so it's very hard to find that. Yes?
So do any of these, I don't know, desirable properties hold for the Sutter space?
You could formulate the same kind of proof for the SCFT, but yeah, I think it's even less clear there. Yeah. You don't. It's not like it's easier to make CFTs dual to gravity in the zeta, right? It's harder. So, yeah. Yes.
What do we gain here if we're replacing strong coupled gravity with CFT?
No, we gained a lot because strongly coupled gravity is a word. Strongly coupled CFT still obeys the bootstrap. We know exactly all the axioms. Okay, so this is, I mean, this is, you can say it to a mathematician. It's a mathematical conjecture. There is a CFT or a family of CFTs with this parameter n, and there's a property on the spectrum. So all the correlators obey crossing. They have a convergent OPE. It's completely well-defined structure, mathematical structure. And now I'm saying that if that is true, then these higher point correlators must take this form. You gain a lot, I think. Yeah. Okay, but well, here I'm not so sure what I should do with this, but well, let's do it more or less quickly. I think all of you know this. So this is, I mean, clearly we need some concrete examples, and I would not be giving this talk if there were not concrete examples, right? So AdS CFT is important because people found concrete examples, like explicit CFTs that are dual to gravity in AdS. So where did they come from, these CFTs? They came from string theory, right? So the only way we know, well, okay, actually, now it's nice that we have these examples of the vector models because they are unrelated to string theory, or well, it's possible to relate them, but a priori they are unrelated. But those are very different. They have this very large symmetry, the higher spin symmetry. But theories that are more similar just with gravity in AdS, we only know how to get them from string theory. Okay, so what's the basic argument that allows us to find basic example? Okay, so. Okay, I'll draw this picture. I think everybody in this room has seen this already, so I'll be very schematic. So how should I ask this? If I ask, yeah, who saw this argument of the decoupling limit of the D3 brane that derives n equals 4 AdS 5 cross S5 well? Who saw it? Okay, I still see some people that didn't see it. Okay, so then I have motivation. Very good. Good. So what is it? This is the only way we know how to get examples. So what's the idea? Let me explain the idea in the most standard example that has been discussed here in other lectures. So the idea is very simple. You just take string theory. So take string theory in 10-dimensional, superstring theory in 10-dimensional flat space, and put some flat D3 branes. Okay. So n of them. N D3 branes. Okay? And this is your system that you want to study. And in particular, you can study processes like, for example, you send in some closed string from infinity, some massless closed string that comes and interacts with this brane. And how does a string interact with a brane? Well, it can open, create some boundary, and then goes off again to infinity. Okay, so for example, this is time is running upwards. So at this instant in time, the string became an open string that is ending on this D brane. Okay, so this is one way of describing this system. This closed string scatters off this D brane. Okay, but actually these D branes are just some solitonic objects in closed string theory. Okay, so you can equally well describe these D branes where open strings can end as a curved geometry. So I'll just remove the branes and I'll just draw some curves like that. So now there's some curved geometry without any brane, and so you can reproduce the same kind of process. So if you want to probe this geometry, you send in some closed string from infinity, but it just comes and it goes back to infinity just because it's moving in some curved background, okay, which is the background produced by these D branes. Okay, so the fact that these two descriptions are equivalent, it's open-closed duality. Okay. And basically now AdS CFT follows from taking the low energy limit of this picture. So we just consider these two descriptions and we analyze what are the low energy excitations in both descriptions. Okay, so let's do that. Let's take low energy. So how do we take low energy? The easiest way is to take so these parameters, number of branes, the string coupling, and the energy we keep fixed, and we just send the string length to 0. Okay, so that's equivalent to focusing in the low energies. And so what happens in each one of these descriptions? So on this side, when you go to low energies, what are the excitations that you have in this system? Well, you have two types of excitations. One type of excitations is just free closed strings in flat 10-dimensional space. And the other type of excitations is just the massless degrees of freedom of the open strings that can live on the D branes. Okay, so the massless degrees of freedom that live on the D branes, it's precisely the field content of super Young Mills. Okay, so this is what you get on this side of the picture. on the other side of the picture, it's more interesting. So obviously, so first of all, let me write this geometry. So this geometry is just, yeah, I'll write it here. So you have the direction of the branes. So you have eta mu nu, dx mu, dx nu. Is it over squared? Yes. And then you have dr is the radial coordinate. So these are just D3 branes. So they have a 6-dimensional orthogonal space, which you can write in spherical coordinates. Okay. And this function h of r is just 1 plus r to the 4 over r squared. Sorry, r to the 4 is just some harmonic function in this transverse space. So it diverges when you approach the boundary. So when you approach the position of the branes that sit at r equals 0. And this parameter r to the 4 is just, I think it's 4 pi g string n times L string to the 4. Okay, so it's a length. It's a length. Okay, so now it's clear. You see, if you just look at this and you take the limit L string to 0, this r goes to 0, h becomes 1, and this just becomes flat space. Okay, so naively, what this gives you is again free closed strings in 10-dimensional Minkowski space. Okay? But this is naive. Why is this naive? It's naive because here, when r is very close to 0, basically, so you have, when r is going to 0, you have an horizon. Okay? So there is a very big redshift between the energies measured by the observer at infinity and local excitations at small r. Okay, so what happens is that there are any local excitation, a local excitation with any energy in the region around r equals 0 is a low energy excitation from the point of view of the observer at infinity. Okay, so to see that more precisely, you can focus on this region. So you introduce a coordinate z, which is just r squared over small r. Okay, and now you send this limit L string to 0, keeping this z fixed. Okay, and if you do that, actually the metric just becomes our friend dz plus dx mu over z squared plus r squared d omega 5 squared. Okay, it's very easy to see. You get from here and from there. So what you get plus the excitations on, so closed strings on AdS5 cross S5. Okay? So for the few of you that didn't see this, any question? Or the other ones can also ask. Okay. So then, with this kind of reasoning, then Maldacena in 97 he just said, okay, let's just cancel these common factors, and then the other two have to be equivalent. Okay, so that's the statement that super Yang-Mills, it's dual to type 2b strings in AdS5 cross S5. And if you're careful with the parameters, you get that the G Yang-Mills square of the Yang-Mills theory is just G string, and the 't Hooft coupling G Yang-Mills square n, the 't Hooft coupling is just the radius of AdS divided by L string to the 4th. Okay, so in fact you see it's a precise realization of this 't Hooft idea. The string coupling you can write as lambda over n, so it's precisely this 1 over n expansion that we discussed in the large n gauge theories. What time do I have? Pi. Good. So, okay, this I'll just say in words because you've seen some examples. So, well, I cannot make justice to the amount of work that is being done in this context, right? I think the paper has more than 10,000 citations now. But let me just say 3 points. So, how can you test this conjecture? Okay. So first of all, this side is again much more solid than this side, right? Here, in principle, this is just a quantum field theory. So we have some non-perturbative definition. In principle, we can even put it on the lattice. Here, we only have a perturbative expansion, at least in G string for sure. But even just at leading, even in the sphere, so even at leading order, in the topological expansion of string theory, this is a hard worldsheet theory to compute. So the worldsheet coupling constant here, the worldsheet coupling is 1 over square root lambda. So it's small when lambda is very large, but at finite lambda it's a hard theory. But okay, that you can do. In particular, you can use integrability to compute many observables. So what can you check? So what you can check is, for example, observables that do not depend on the coupling. Then you can compute here at weak coupling and here at strong coupling where the worldsheet is weakly coupled, and then they just match. For example, the 2-point functions and 3-point functions of half BPS operators. Okay, so those are examples that you can just compute. These different computations, they just give the same number. They don't depend on the coupling. Then you can compute things that depend on the coupling, but they still have lots of supersymmetry, so you can compute them using localization, for example. Okay, so examples of that is the partition function on an S4, or the expectation value of circular Wilson loops. So you can compute in super-Young-Mills at any value of the coupling, and you can match with what the strong coupling prediction from string theory gives you just by computing some, either from supergravity, the partition function in supergravity, or from some worldsheet calculation and minimal area calculation. And then there are other things like Pedro is talking about, like the dimensions of operators which are non-protected, or scattering amplitudes in the planar limit, or even now 3-point functions in the planar limit between single trace operators. Okay? So all these quantities seems to be possible to compute them at any value of lambda in the planar limit, and then you can take lambda to be large and compare with a worldsheet calculation, and it works. Okay, so and there are many other tests, but usually, I think in this context, all the tests that exist usually involve either observables that are protected by some supersymmetry, or that you can compute using integrability. There is no real test like in some black hole domain or some region, some observable that really tests more chaotic dynamics of the theory. Okay? Although there are other tests, not in this theory, but in theories that are more lower dimensional versions of this conjecture. Okay? I should stop, no? How much time do I have? Okay, but I should not come back to this next time. So let me just 2 minutes, okay? I already 4 minutes too much, okay. So the only thing I want to say, this I don't need to say, it's pretty obvious. So all the properties, so you can check that it obeys this relation that we found generically. If you measure the Planck length, the 5-dimensional 5D Planck length, it scales like n squared when you go through the map. And the other important parameter is that you have this delta gap for the higher spin fields, which corresponds to massive string states. So basically this goes like the mass of the string in AdS units, which is just R over L string, which is lambda to the 1/4. And using integrability, you can really compute from weak coupling and see these parametrically large anomalous dimensions for all operators that are not protected. So that's something that fits the generic picture. So what is different from this pure gravity CFT that I was discussing up there? So the main difference is that here the dual is not pure gravity in AdS, it's supergravity in AdS 5 cross S5. Okay, so you both have supersymmetry and you have a very large internal space. Okay, so the radius of the S5 is as large as the radius of AdS. Okay, and so these 2 points, both SUSY and the fact that you have large internal spaces, I think it's not known if they are general or if they are just an accident that the simple theories that have more symmetry that we can actually find explicit examples have. Because the examples we know in string theory, they all have or a lot of supersymmetry or some weak breaking of it, some orbifold or some, but they are really closed cousins. They are not purely non-supersymmetric theories. Okay, so supersymmetry from the generic point of view of our discussion didn't play any role at all, but in the concrete example seems to play a very important role. So I think it's an open question if it's really crucial or not. It shouldn't be. I think it should just make it easier. So that's why the examples we know have supersymmetry. But it's unclear because since we need lots of strong coupling, maybe supersymmetry is important to stabilize the theory when you go to very strong coupling. So it's an open question. This is another open question. Can you find a CFT which UV completes gravity or even supergravity, but just in lower dimensions? So let's say even in 4 dimensions. So for example, n equals 8 maximal gauge supergravity in AdS 4. Can we find that? It's not known. Whenever we find a CFT dual to some supergravity, it's always either 10 or 11 dimensions. So it seems that the CFTs want to describe gravity in a bigger space. So there is some work trying to make string theory constructions where the internal spaces are very small. There's some paper by Polchinski and Silverstein and some recent work by Quevedo and collaborators. But it's very unclear at the moment if it's really possible to construct CFTs which are dual just to AdS without a big internal space. Okay, and I should finish here. Thank you.
So in terms of this generic thing, where does your paper with Polchinski and Solly fall in? I thought they were kind of
So good. So what we proved is that, okay, let me try to make it fast. So if you have a large n, so suppose basically you assume that you are from the infinite n limit. So your 4-point function is just the product of the 2-point functions. And now you want to say, what are all the possible solutions to the bootstrap equations, to the crossing equations, at order 1 over n squared? Okay, the first correction to the 4-point function. So what are all the space of all consistent 4-point functions that can correct this free theory at order 1 over n squared? Okay, and basically we showed that this space is in 1-to-1 correspondence with local quartic vertices, with interactions that you can write in AdS. So any solution to crossing, at least perturbatively in 1 over n, can be just found by taking AdS and putting some vertex by hand. Okay. but this is not sufficient to tell you. So in particular, it's an infinite number of solutions. So let's just take the scalar field. So we're analyzing the 4-point function of this scalar operator, and so it starts with plus permutations, right? Which starts with disconnected piece plus 1 over n squared. And this is where you will find all possible solutions here, right? All possible solutions to the crossing equations that can complete this 4-point function, okay? And basically we found that it's a one-to-one map with putting interaction vertices in AdS of this form. So it's quartic vertices, right? Because you want to construct something that corrects the 4-point function, okay? But it's quartic vertices with many derivatives. Okay, so you can put here many derivatives and contract them, whatever, some way. Right? Contract them all, make some vertex, and put in the AdS action. Given a vertex like this, you get a Witten diagram, and that's a solution to crossing. Okay? But you see, here, they all appear as solutions, but the point there is that solutions with more derivatives should be suppressed, so this should be suppressed by delta gap to the number of derivatives, right? From an effective field theory point of view in AdS, to generate this higher derivative interaction, this should be suppressed by the mass gap, by the high dimension particles that you are integrating out, because you're only describing an action for these light fields. Okay? And this we didn't say anything about. It's actually hard to say anything about because all this is extremely small because it's already 1 over n squared. So usually you argue that this has to be suppressed because when you go to high energies, these things grow and you have to suppress by the cutoff. But here, everything is multiplied by 1 over n squared because it's a classical statement. So that argument just like that doesn't quite work. So that's why you have to go through these more indirect arguments of studying scattering of gravitons to show that you have negative phase shifts when you reduce the impact parameter, and these higher derivative terms actually are bad for causality. It's not enough to have just an effective field theory argument.
Let's be back at the 10 to 4.
Does this result in any dimension?
Yeah, absolutely.
I think so.
R squared terms that was topological.
If it's in very low dimension. If it's very low dimension, there's only 2 structures. In bulk 4 dimensions, there's only 2 structures. But for sufficiently high dimensions, it's okay.
How do you derive this scaling?
Okay, I was supposed to do that, but given the lack of time. So where do I have it? Do you want this board?
I mean, this one.
No, but yeah, how does that come about? Let's do it here. So let's look at the action of type 2b.